let's take a look at an example problem that involves the frequency response. This is problem 4.8-1, and we're given the following system transfer function: s plus 2 over s squared plus 5s plus 4. We can factor the denominator as s plus 1 times s plus 4. It's not actually necessary that you do that factorization here. The frequency response we can obtain by just substituting in j omega for s everywhere. So j omega plus 1 and j omega plus 4. And I want to find the magnitude response and the phase response. So the magnitude response of the system is the magnitude of this complex function of omega. So the magnitude of a product of complex values is the product of the magnitude. And so magnitude of the numerators, the square root of the sum of the squares, or omega squared plus 2 squared, or 4. And then similarly for the denominator terms, the magnitude of j omega plus 1 is omega squared plus 1 squared. And then for this last term I have omega squared plus 4 squared, or 16. Notice here that when I'm finding the magnitude, it's the imaginary part of the number, which is just omega. The imaginary part is not j omega. So the imaginary part squared is omega squared, not j omega squared. That would actually lead to a minus sign. So this is the magnitude response. Notice that it is a real function of the real variable omega. There are no j's embedded in here. So, you know, I could plot this pretty easily using any sort of graphical computer software, evaluated on my calculator for different values of omega pretty simply. Let's turn to the phase response. The phase angle of a product of complex values is the sum of the phase angles, and similarly the phase angle of a ratio is the difference. So the angle of 2 plus j omega in the numerator, I can actually, on the complex plane, this would be, for example, 2. Omega might be anywhere on this axis, so this would be the point 2 plus j omega. So the magnitude is this distance. So that distance would be the square root of the sum of the squares of the side, or square root of omega squared plus 2 squared, which led to this value. This angle, this is the phase angle. It's the counterclockwise angle from the real axis here. This angle from basic trigonometry is just the inverse tangent of this side, which is the imaginary component, over this side, which is the real component. So more simply, the phase angle of a complex number is just the inverse tangent of the imaginary part over the real part. And then now I subtract the angles of the denominator terms, omega over 1, or just omega, and then finally the inverse tangent of omega over 4. Again, this is a fairly complex function, but easy to evaluate on a calculator at any particular value of omega. I could graph it fairly simply using Octave or MATLAB. And in part A of this problem, which is the only part we'll do, we're asked to find the response to this particular input. So 5 cosine of 2t plus 30 degrees So it's a sinusoidal input with a frequency of 2 radians per second. So I just need to evaluate the magnitude response at 2. This would be 4 plus 4, 4 plus 1, and then finally 4 plus 16. This reduces to square root of 2 over 5. Okay. And then similarly for the phase angle, I can substitute in omega equal 2 and evaluate this. The result is the corresponding phase angle is minus 45 degrees. Alternatively, I can just, if you've got a calculator that handles complex numbers, I can just substitute omega equal 2 into this expression and have the calculator show the result in polar or exponential form and get the magnitude and phase directly. But now I've got the magnitude response at this frequency of 2 radians per second and the corresponding phase angle at 2. So the output then is just the amplitude of the input times my magnitude response, square root of 2 over 5. And then I have, at the same frequency with the original phase angle plus the additional phase angle introduced by the system, which is a minus 45 degrees. So I can write this in a slightly more simpler form as cosine of square root of 2 cosine of 2t minus 15 degrees then. Let's take a look at the frequency response of two systems we've dealt a lot with in the past. The ideal differentiator this frequency response will provide some additional insight into the differentiator. The transfer function of an ideal differentiator is just S. Multiplication by S corresponds to time differentiation, and then so define the frequency response, then I just substitute j omega for S, and I'm left with the frequency response is equal to j omega, corresponding magnitude response is just equal to omega. This is an entirely imaginary, so no real part. So the magnitude of this is just omega, and the phase angle here, because it's entirely imaginary for all frequencies, this would just be equal to plus 90 degrees. So I could graph these quite simply. In this case, magnitude response is just a straight line equal to omega. So for example, at a frequency of 10 radians per second, the magnitude response is 10, and the phase angle here is just plus 90 degrees at all frequencies. So that's omega. This is the angle of hj omega. Okay. So let's take a look at the case where, for example, x of t is cosine of 10t. Okay. I can immediately get the output of this differentiator system. It's going to be cosine at the same frequency, but now at a frequency of 10, the magnitude response is 10, so the amplitude of the output is the amplitude of the input, which is 1, times my magnitude response, which is 10, and I have cosine of 10t, corresponding phase angle is plus 90 degrees. If I shift a cosine by 90 degrees, that's a shift to the left. That actually becomes a minus sine of 10t. Cosine of 10t plus 90 degrees is minus sine of 10t. And so so either of these forms is acceptable. but I can write the output as just minus 10 sine of 10t. Again, this is a differentiator. We got this result by actually finding the magnitude response at omega equal 10 and the phase response at omega equal 10. But another way to find the output of this system is just take the derivative of the input. The derivative of cosine 10t is, pull out the omega part, would be 10. The derivative of cosine is minus sine, and we directly get this result. Another thing you can see from the magnitude response is that the magnitude response increases with increasing frequency. So, the derivative of cosine of 100t would be minus 100 sine of 100t. And if the input were cosine 1000t, the output, even though the input amplitude is only 1, the output would have an amplitude of 1000. So a differentiator, as you can see here, really amplifies high frequency input signals. Let's take a look at one more system, the counterpart to the differentiator, the Ideal Integrator. The Ideal Integrator has a transfer function of 1 over s, so the frequency response is 1 over j omega. I can write this, multiply numerator and denominator by j. I'll get a minus sign in the denominator, and that leads to minus j over omega. So the magnitude response, again, this is entirely imaginary, but the magnitude response here is just 1 over omega. The phase angle of this, the integrator, is actually minus 90 degrees. So in a plot of these two functions would look like this. This thing goes to infinity at omega equals 0, but then decreases for increasing omega. So at a frequency of 10 radians per second, the magnitude response is 1/10, and then the phase angle is minus 90 for all frequencies, omega, h, j omega. So again, we could take a look at, for example, the same input I had before. X of t is cosine of 10t. You can immediately write down the output. In this case would be 1/10 the amplitude of the input times my magnitude response evaluated at 10. Cosine of 10t minus 90 degrees. Cosine of 10t minus 90 degrees. This is cosine shifted to the right by 90 degrees is just sine of 10t. And again, we can see that this is actually the integral of cosine of 10t. We can also see from a plot of the magnitude response that as we go up in frequency, the output of our integrator is going to be smaller in amplitude than the input. So an integrator tends to suppress high frequencies while amplifying lower frequencies.